In today's video, we're going to look at how to numerically solve the energy eigenvalue equation. In the last few videos, we've been looking at the infinite and finite square well potentials in the position representation and trying to get through the process of how do we figure out what those wave functions are and what those energy eigenvalues are given those potentials. We also spent a bit of time looking at just sort of what we would expect for an arbitrary or asymmetric potentials, um, and how to think about that. But it turns out a lot of the times, even if we do follow that, we can't get analytical solutions to the energy eigenvalue equation, and we have to resort to numerically solving it. And that's what we're going to look at today. Um, Essentially, what we're doing is solving that differential equation in the position representation. And we can look at, to kind of see how this is all going to work, we're going to look at a lot of classical physics examples of solving differential equations. The one you're probably most familiar with is Newton's second law when you have a constant net force, F equals ma. That differential equation becomes the second derivative of position with respect to time is equal to F over m, some constant. And the whole goal is to find that position as a function of time. We can solve this just with simple integration. You get your first kinematic equation, the velocity as a function of time is equal to the initial velocity plus the acceleration times time, where that acceleration is the constant we got from Newton's law. Integrate that again, and you get your position as a function of time. The whole goal, initial position plus the initial velocity times the time plus 1/2 at squared. Hopefully we're all familiar with this from intro physics classes and that. One of the main points, though, is we can do this, and pretty simply, because that second derivative is equal to some constant, we can just integrate it out. It has a nice, the differential equation has a nice form that we know how to solve analytically. If you think of our energy eigenvalue equation, it looks like this. And when we rearrange that, so the second derivative is just on the one side, we have the second derivative of our wave function is equal to a whole bunch of stuff out front times our wave function, right? And this is sort of, it's similar in the sense that it's a second order differential equation, but we can't just do that integrating out, right? There were a few examples where with the infinite well and the square well potentials that we've looked at, where depending on what this v was, we could do some separation of variables, and we were able to solve it analytically. It was slightly more complicated, but in general, our second derivative depends on the variable that we're kind of trying to solve as a function of. It has that wave function on both sides, but it has, more importantly, it has this potential energy term here that depends on position as well, which can make things very complicated and essentially unsolvable analytically for many cases. So what we're going to do today is look at, well, how can we use this equation and solve for that wave function in those situations? And we're going to lean, again, as I've mentioned, heavily on this classical physics sort of example, because it turns out you can take essentially these classical physics examples and work backwards, sort of thing. So that's what we're going to look at today. We'll walk through and kind of compare the two and hopefully give you a bit of an understanding of how we can do those numerical solutions, and then work on some in the homework or in synchronous class, in our synchronous meetings. So to see how this is all going to work, let's start with a classical example, and let's just start with looking at what the answer that we're trying to find is. So let's say we have some position as a function of time that has some kooky dukes thing like that. We don't know what the position as a function of time is, but the answer is going to end up looking like this, and that's what we're trying to figure out. This is position as a function of time, and this is our time. And the whole goal is to figure that out. What we do know is, let's say we have our object, we know its value at the initial, where it started. We know where this thing began. And, just to add to that, let's say we also know our initial velocity and our initial acceleration. Okay, so we know those things. And what we're trying to figure out is what this position as a function of time is. Well, we re we remember from the case where it was a simple position as a function of time that we solved in the initial case. We knew that our velocity at some time t was equal to the velocity just before it plus some acceleration times t. And we knew that our position at some time t was its initial position plus its initial velocity times some delta t plus 1/2 a delta t squared, right? We can actually use these to get this function, even though this function clearly doesn't have that constant a that we're looking at. And the way we do that is if we zoom in on this part of our plot, what is this actually going to look like, right? If we blow up that region, it looks like this. Let me see if I do it. It's going to look something like this, right? So that is that region in that box. We'll say it looks something like that. So again, we have our initial point here. That's x0 times t equals 0. And what we're trying to do is basically draw this out. Well, one of the things we can do is say, okay, we're going to look at some very small delta t. We're going to keep this very small, and provided this delta t is quote unquote small, these equations will work, because if we go from here to here, there isn't that acceleration, the curvature of this function. Remember that a is equal to the curvature of the position as a function of time. This curvature doesn't change much, right? It's not, getting steeper, shallower. It doesn't change much along here. So we can make that assumption that the a is constant, which makes these equations work. So if we wanted to find out what this position, a x1, t1 is, we can use those equations. And what we would say is, well, x1 is going to be x0, the position here, plus v0 times delta t plus 1/2 a0 times delta t, right? And what that is, it's I started here. Let me switch colors here so we can see this. I started here and I knew the slope. So if it was just that slope line, I would have had to add this delta t times the slope to get me this term. And if it had some curvature to it, I would have added this, and that would have added, a bit to there. But the gist is, I use that equation. I now know this point. Now, what I have to do is say, well, that was using the velocity and acceleration at t equals 0. I need to update those, because now that I'm here at x1, the position, the slope has changed and the curvature has changed slightly. So I need to figure out what v1 is. And that's going to be equal to, well, v0 plus a0 times delta t, right? Whatever this delta t is. And now it gives me my v1. Now, typically, in these classical physics examples, like the reason that we get these weird sort of position as a function of time is because our acceleration is changing as a function of time. Clearly, this curvature is changing in here. So we would also have to update our acceleration. And typically, that acceleration is going to be as a function of time, or it's going to depend on these velocities. It's going to be determined by Newton's second law, which will depend on the position and the velocity it's going at. So this is actually going to be a function of one of those two things, or both of those two things. So given that I know v1 and v2, now I can say, all right, my acceleration 1 is going to be whatever that function is with those new updated values determined here. So now I have a1 as well, and I'm in the same position I was here, and I can then take my next step of delta t over here and use these same things and get my, oops, too far. and get my x2 is equal to x1 plus v1 delta t plus 1/2 a1 delta t squared, and then redo the v2 is equal to v1 plus a1 delta t. And then finally, a2 is going to be a as a function of, well, whatever that v1 and x1, v2 rather, and x2 that I just updated. So, and then we can step through this whole function, and what you'll see is what ends up happening is you get here and you've slowly calculated these points, and if you do delta t small enough, you're going to map out that whole function, right? And you'll get your, ultimately you will draw out your solution x of t, which was the goal of solving that differential equation. One thing we have to note here is delta t small enough actually means something. If you choose a delta t that's too big, say my delta t went from here to here, right? You're going to assume this is going to make that, you know, the curvature is changing in here. Likewise, the slope. So these assumptions that the accelerations are constant aren't good for a large delta t, right? It's clearly going to cause some error in here, and I don't know if it'd be high or low, but you would be off, right? So you would get something like this, and then the whole solution would not look like this. So you have to keep delta t small. And by small, we mean the change delta t is small, smaller than some value, whatever, call it eta, that the acceleration at t is approximately equal to the acceleration at t plus eta. Right, where you know, so this, you know, is a rough way of sort of saying, all right, as long as my step size is small enough that they're about the same, the uncertainty, or the error rather, I should say, in this numerical solution will still be small. And really, one of the ways to do that, there's a bunch of techniques we won't get into in numerical methods that can sort of adapt to that step and that. But one of the simple ways to do it is make delta t smaller. And if your function isn't changing as delta t gets smaller or bigger, then that step size isn't affecting your solution. It's kind of getting you the right answer. As you make it bigger, if your solution starts to change, that's the point at where you have to consider, okay, my step size is too large.
Another way we can improve this sort of algorithm has to do with how we are doing our update equations here, right? Typically, or in a lot of cases, and the ones we're going to use with for the energy eigenvalue equations, this curvature, the second derivative or acceleration in this case, is actually only dependent on position, the function we're trying to solve for, not its first derivative. And if that's the case, we can actually improve how we update our velocity, right? If you think about it, we get our new position x1 by essentially assuming the acceleration and velocity a1 and v1 are or a0 and v0 rather, at the start of that time interval remain the same for that whole time interval, which is a reasonable assumption, but we can do better. If you think about it, if we knew the acceleration at the end of that interval and the start of that interval, the average of those two would probably be a better estimate for what the acceleration is in that interval. And since this acceleration is just some function of the previous, of the position at that point, if we calculate this first, we can then calculate this and use the average acceleration for the update of our velocity, right? And that will improve the accuracy of our results. To see what I mean, or to just write that out explicitly, our update equations in this, using this sort of modified technique, which the book refers to as the velocity of Rayleigh algorithm, is, you know, if I want to find the nth position, it's just going to be the nth minus 1 position plus the nth minus 1 velocity times delta t plus 1/2 a n minus 1 delta t squared, right? That's the exact same thing we just had. But once I calculate that updated position, I can then calculate an updated acceleration because I have the functional form of that acceleration, and all it does is depend on position. So now I have that updated one. Then I can kind of go to update my velocity by using our update equation. But instead of using the n-1 acceleration, I'm going to use what I'm going to call just that sort of average acceleration, which is going to be equal to n-1 plus, this is going to be the updated acceleration plus the previous acceleration, all divided by 2 times delta t, right? So this is sort of an improved update equation for our velocity. And then I've got sort of our position, velocity, and acceleration at the next point. And ultimately, again, what we're doing here is we're trying to get this position as a function of time function. And all we know is sort of the initial conditions, x0, v0, and a0 at t0, and then we step through and get updated points, and eventually, whatever that is, we should be able to simulate that and draw out the actual x of t we're looking for. So how's this going to help us with the problem we're actually trying to solve now, the energy eigenvalue equation, right? So just to sort of draw the connection between the two, in this classical example, F equals ma gave us our differential equation, the second derivative with respect to time of x of t was equal to some acceleration. And to be honest, we could have it as a function of time in this case, right? So we knew Newton's law gave us some function for our differential equation, and we use these update equations to sort of step through that. What we're trying to do now is solve what we get from our energy eigenvalue equation in the position space representation, where we have the second derivative of our wave function is equal to negative 2m e minus v of x over h bar squared times that wave function as a function of x. Where one of the key things is the potential energy depends on position, right? So mapping those, in the classical case, we were trying to solve for x of t. In this case, we're trying to solve for phi of x, right? And in the classical case, our acceleration was a function of position. And in this case, our, our curvature, or our, I guess I'll just say dx dt squared, depends on this position here as well, right? So this is a function of position. I guess I'll just write it like this. So what are we going to do? Well, essentially, if we have, let's just draw some, well, let's use the example that we had, the asymmetric well we discussed in the last video. If our well looks something like this, say, and say we're trying to solve one of these energy eigenvalues, whatever, E3, right? We know that in the boundary, it's going to exponentially decay, and it's going to have a shorter wavelength on this side and then a longer wavelength on the right because of the connection, then an exponential decay. So this is kind of sloppily drawn, but we've got 3 antinodes, whatever. But we kind of know it's the wave function phi of x is going to 0 if I'm deep enough into that barrier, where this is, some finite barrier that looks like this. And so I'm going to essentially take this boundary condition, and I'm going to assume, this is decaying, so it's still got some, my first derivative of that wave function is going to be small, but non-zero. And I'm going to say it's essentially flat at there, equals 0. and this equals 0, deep into that boundary. And then I can use this sort of, these update equations to step through there and draw out, you know, what that wave function will look like. To do that, I'm essentially going to use the update equations, right? So I know phi of at some initial x point, I know the derivative at the initial x point, and I know the second derivative at that initial point, whatever we're calling this x0 that we want to start our sort of numerical solution at. So if I have these sort of initial or boundary conditions, then I can figure out what my, if I step in some delta x and I want to know this point, phi 1, I can determine that using the update equations. It's just going to be phi 0 plus that first derivative at phi 0 times delta x, whatever that step was, plus 1/2 the second derivative at 0 times delta x squared. And now I have my updated wave function at some delta x over, just like we had up here in the classical example, where I figured out my new position based on my previous position, my previous velocity, and my previous acceleration, first derivative and second derivative. I'm doing the same thing down here, right? Now I'm going to use this modified Verlet algorithm. I'm going to calculate the second derivative at the updated position just by putting in, you know, this equation. This is my function of phi of x, right? It depends on x and a phi. So I can calculate that. I'm just going to write it this way, phi of 1, right? So now I have an updated that, and I can update now my first derivative by using this same Verlet type of algorithm, where it's my first derivative at the previous point plus the average of my second derivatives over those points divided by 2 times that delta x again. Remember, we're stepping through this axis here, which is x, not time like we were in the position. But we can sort of just walk through updating these wave functions as we step through. And again, we're going to get something that looks like this. Now, there's an issue in that we don't know everything here. We don't know the energy. So we kind of just take an initial guess, right? And see, we thankfully, after, you know, all the sort of discussions we've had on the wells and asymmetric wells we know we know that this bound state has to sort of fit inside our well, and we know roughly what we expect it to look like. So we can take an initial guess that we use in our function here. And when this, you know, numerical, when we run through this algorithm, we'll get something in here, and we should kind of almost immediately tell if that's a valid solution or not. Like if our solution ends up looking something like this, we know that's not the right solution we were looking for. So then we would change our energy, our guess, and we have a good guess. We know what this V naught is in terms of energy, so we can sort of say, all right, if this is 0, that's V naught. We're looking for an energy somewhere in this range, and we should be able to guess a reasonable energy here, get something close to here. Sometimes you'll see it go off in a certain way, so you'll have to adjust it slightly to make it kind of come down further. But the point is, we can make reasonable guesses here, run through our algorithm to step through all this, and then plot that result and see if it's giving us something reasonable. And you can kind of put a nice bound on what those energies are, because, you know, if you're off in one direction, you're going to see this curve up. And if you start to, let's say, lowering it starts to stop this from shooting off into the barrier, when you get too far the other way, it'll go down, and you can kind of bring these closer and closer together and say, all right, I know it's between those two values. That's my eigenenergy. And I know the wave function has that sort of form. But anyway, this is a sort of a technique to numerically simulate what these wave functions are and determine what these eigenenergies are. And if you remember, this is kind of one of the big points of using the position representation is we want to know what those eigenvalues for the energy eigenvalue equation are because they come into the time dependence of that system and all of those things. So we need a way to actually calculate them theoretically. We do that by solving that differential equation. A lot of the times that can't be done analytically, so we have to do it numerically. So that's kind of the broad overview. We are going to go through this in the synchronous classes and homeworks and try to get through some examples with this.